Okay, now we're on to chapter 3. Now we're going to be talking more about organic molecules, like that. So one of the things you're going to need to do is we're talking about what are called functional groups, like that. So that's where a lot of the chemistry is going to happen throughout the rest of this course, like that. So there is a table 3.1 with that. So that is a chart you're going to need to know. You're going to need to know the name of it as well as the general structure. So a couple of different things you can do, right? Is you can look for you can look for non-carbons within the structure. That's typically going to be where something is, and then also the double bonds and triple bonds or whatever, especially double bonds that aren't associated with a benzene. Benzenes are here, so they are these six-membered rings, right, with alternating double, single, double, single, double, single. This is what they basically have to look like. If they look like something else, then they're going to they're going to be just regular alkanes, stuff like that. So, right. So if I give you a molecule like this, right, stuff like that. So what are you going to do? So what I typically ask, right? So it's a circle and name the functional groups for the molecule, right? So for that. However, usually just strict alkanes, right? Just regular chains like that. You don't have to worry about cycloalkanes, which are cyclic, right? Go in a ring, but you don't typically have to label those. So this would actually be this triangle here. This is actually an example of a cycloalkane, right? Just all single bonds, right? But coming back in a ring. We'll talk about that next chapter. And arenes, which are another, which in general are basically benzenes, right? So this is a benzene here. This is a benzene there. That's a benzene there. Benzene, benzene. And this is a benzene here as well. So like that. So this is an arene, but you don't have to just worry about it. But I don't need you to know those. So like that, because it gets really hairy. So like that. What I'm going to need to know are the other functional groups. You do need to know them, but you don't necessarily have to answer them for the test. And on an exam, it would say exclude those particularly. So like that. So what you would do, right? So you would go along in here and look at the functional group, right? So there's a non-carbon there and there, right? Stuff like that. So you have to be very, very careful with the C double bond O's. You have to look on either side, right? It depends on what's going on, right? So if it's carbon on one side, that equals a ketone. Ketone, right? So if you have carbon on one side and an OH on that side, that's a carboxylic acid. Right? A carbon, C double bond O, carbon on one side and O and another carbon, that's an ester. Carbon on one side, but say the nitrogen on the other side, that's an amide. Carbon on one side, right? Cl on the other, right? So you have C double carbon, Cl, right? So this be an acid chloride. Okay, there's going to be several of them like that. All right, so whenever you see a C double bond O, you have to be very, very careful to see what's on either side, and it's the whole group, right? So this is a ketone, that's a carboxylic acid, this is an ester, amide, acid chloride. All right, so this is an amide, or excuse me, this is an amine, because it doesn't have a C double bond O next to it. But this C double bond O has a nitrogen next to it, so this is an amide. Okay, so you have to be careful the difference between an amine and an amide. And this isn't a ketone and an amine. It's an amide because it all works together, right? So alcohol, C double bond O. Again, we have to be careful. Carbon on one side, OH on the other. So it's a carboxylic acid. Same as this one here. This one is just just a chloride all by itself, right, hanging off a benzene. So this would be a chloride or a halide, either one. This is a nitrogen without a C double bond O next to it, so it's amine. Sulfur, carbon, sulfur, right? So this would be the sulfide, right? So carboxylic acid, alcohol, stuff like that. So just be careful, stuff like that. So and there'll be some practice problems for you as well, stuff like that. So what I want to be able to you guys to do is we're gonna need to know these, because these are going to be the groups that we use throughout the year. But also, it's always kind of fun to look at the packaging if you get a pharmaceutical drug from the pharmacy. Sometimes they have these structures in here. It's kind of interesting to see the type of functional groups that are in there. So, okay, so after the functional groups, right, we're going to be talking about the simplest form of carbon compounds, and those are alkanes. Like that. So alkanes are we sometimes just call them hydrocarbons, right? So they're just going to be carbons and hydrogens, at least at this point. Like that. Eventually, we're going to put functional groups on them, but they only contain carbon-carbon single bonds, carbon-hydrogen single bonds as well. Something like that. So all the carbons are if you look at it, if you calculate it, they would all be sp3 hybrid. Something like that. So the general formula for every one carbon you have 2n plus 2 hydrogens to it. Like that. So that's the general formula. You'll sometimes hear them called saturated hydrocarbons, right? Because it only contains single bonds, right? So if you had, if you buy saturated fats, basically they've had all of there's no double bonds in there. Stuff like that. So it's sometimes also called aliphatic, which is Greek for fat. Stuff like that. So you can also call it aliphatic sometimes. Okay, so isomers. Okay, so you remember what isomers are? They're compounds that have the same formula, but have different arrangements in space. The atoms have different arrangements in space. Sometimes they're called constitutional. There's different. When we're talking about here, constitutional isomers, right? So you can have pentane, which has we'll get to the name, which has 5 carbons in it. Okay, you can either have them all in a row, or you could do 4 in a row and then one off here, or you could do 3 in a row and then two of them hanging off on either side, right? So they all have the same formula, right? But the arrangement of the atoms in space is different, right? So these are called isomers, right? So this is sometimes called a straight chain alkane. This is sometimes called a branch, right? So this would be the main trunk of the tree, right? And you have branches coming off of here, like that. So these are also sometimes called normal alkanes. Okay. So again, here are the names of the different lengths of carbons that we talk about, right? So you need to know this from 1 to 12. Okay, that we're going to be using these the rest of the year, so we need to go ahead and memorize them now. Something like that. So methane, ethane, propane, butane, right? So that the first 4 have sort of historical reasons why they're named that, and the rest are pent for 5, hex for 6, sep 7, whatnot, all the way down to 12. So like that. So methane actually comes from the Greek for wood, because they used to when you would make methanol, you can isolate methanol from wood alcohol, stuff like that. So that's what alcohol is, right? So like that. So because it's 1 carbon long, they call a 1 carbon piece methane. Ethane. Stuff like that. So the for propane, it was the one that. So this was the first compound, stuff like that. So that it's propane. So it actually comes from first fat. So this is propanoic acid, which was 3 carbons long. It's a carboxylic with a carboxylic acid on it. It was the first one that wasn't completely immiscible in water, stuff like that. So butane, it actually is the first. They used to be able to isolate butanoic acid, which is a 4-carbon carboxylic acid, for rancid butter, right? So that's where these names come, and then the rest of them are just going down sort of the regular Greek roots for the numbers, so like that. So you do need to know those, right? We're going to be using these a lot with that. So okay, so organic drawing shorthand, stuff like that. So again, if you have something like butane, right? So it's 4 carbons, right? So if you want to show all the bonds here, you could do it like this. If you want to represent the tetrahedral nature of the carbon bonds, right, you can sort of you can put these in this sort of sawtooth pattern for the carbons here, right? You can do a condensed structure like this. We're showing the single bonds or just squishing them all together. So you assume that they're carbon bonds between here, here, and here, and here, right? So don't forget, right? So this is saying that these three hydrogens are on that carbon, just like that. You can also sort of abbreviate, if you have a long chain like this, you can also say, well, I'm going to put these all together and we have a CH3, and then what this would mean next is that we have 2 CH2s in a row and then a CH3. For butane, it's not, usually don't write it like this, but if you have something that's 20 carbons long, right? So you could say, instead of writing C out, you could do CH3, right? And then you would have CH2, you'd have 18 of them and then CH3, right? So if it was 20 carbons long, right? So that's a nice way of abbreviating it, like that. So you don't have to keep writing out all 20, like that. So if you have all your carbons in a row, okay. Sometimes this is called so it'd be butane, right? But what we're saying is you have the normal isomer for butane, so N-butane, normal butane, as opposed to, right? So back here, this would be considered normal pentane, right? 5 in a row. But if you had a pentane isomers, right, you would have branch. So these would be different. These would be non-normal. Right? We'll talk about that later. What you would call those, right? But this would be in normal pentane or N-pentane, right? Just like this one would be in normal butane, right? This is just regular four carbons in a row, so we call that N-butane or normal butane. So okay, so when we're talking about branched compounds, right? So like that, so the branches off the main chain. One of the things that we'll do is we're going to be using these names a lot, like that, right? So like that. So but what we'll do is if it's the A and E, that means that we're talking about how many carbons are in the trunk of the tree, the main chain. We'll talk about that in a minute. Main chain, stuff like that. But if we also have carbons branching off, right, we have to indicate that. And then what we do is we take the A and E, right, and swap that for a YL, right? So if you have a 1 carbon piece coming off of the branch, you would take methane, take off the A and E, right? So if you had, say, this compound here, right? Right. So here's the main trunk of the tree, right? And then you have your branch here. So it's 1 carbon long, right? So it'd be methane. Methane. Take that off, and you add Y, and you substitute YL. So a 1 carbon piece coming off of there would be methyl, coming off of the main chain. So if it's a 2 carbon piece, it would be methyl. A 3 carbon piece would be propyl. The 4 carbon piece would be butyl. 5 carbon piece would be pentyl, and so on and so forth, like that. So A and E suffix means that it's the main chain. The YL means it's a side chain. It's a group that's branched off from the main chain, from the trunk of the tree, like that. So okay, so with that, you can sometimes see these for different alkyl groups. So the problem is, if it's small, there's only one. There's only one way that you can put it on there. But for propyl, right? So when you have a propyl group, right? There's actually a couple of different ways. So if this was the main chain, right? Right. So if you had carbon, 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 right, coming off of it, right? So it's 3 carbons long, right? So it'd be propyl, right? The problem is, another way that I could write this is if again it's 3 carbons long, but instead of connecting at carbon, if you number these 1, 2, 3, 1, 2, 3, right? Instead of connecting at carbon 1, now it's connecting at carbon 2. Okay, so the way that we designate that would be, we would say this would be technically a 1 propyl group, or sometimes we just shorten it to propyl. We just sort of assume it's 1, but you could put 1 propyl, okay? Or to indicate that it's connected to the to carbon 2, we're going to say that it's a 2 propyl group. Or sometimes this is called an isopropyl group. Okay, you'll notice that one of the things I do, if you're separating, you want to separate a number from a letter, you do a little dash. So it's not that big of a deal, but typically that's how it's done. If you want to separate numbers, you do a comma. If you want to separate a number from a letter, or vice versa, you use a dash between it. So like that. So this is sometimes called isopropyl, but really what it's a better name would be 2-propyl, because it's saying it's a propyl group, right? It's 3 carbons long. The branch is 3 carbons long, but it's connecting at carbon 1, right? If you have 1, 2, 3, right? So for this one here, again, it's a 3 carbon piece, right? 1, 2, 3. But it's connecting at carbon 1, right? So technically this would be a 1 propyl group, or just a regular propyl group, something like that. So now butane gets a little bit more difficult, okay? Because again, you can have, right? So you can just have right? So it's a 4-carbon piece like this, right? So C4, right? So it'd be butyl, right? Right? The YL indicating that's a branch, right? But again, right? So we have 1, 2, 3, 4. Another way you could say it is actually 1 butyl, right? Because again, right? Right? So if we connect it at carbon 2, right? So it'd still be butyl, right? But now it's connecting through carbon 2 to the main chain. So now it's 2 butyl. Okay, or sometimes it's called sec butyl. I don't typically like these names. I like this one here because it's more descriptive. But sometimes you see this sec butyl or secondary butyl. Sec equals secondary. Okay. Now, the other thing that can actually happen is, what if we have here? Now, it's still 4 carbons, right? But the main chain of that carbon is 3 long. So, right. So what we do. So this one is technically, and we'll talk about this more when we do the proper naming, is actually 1. Right. So it's actually 2 methyl, 2 propyl. Excuse me. Actually, at least written like this: 2 methyl. No, I'm sorry. 2 methyl, 2 propyl. Right. So it's a propyl group. Right, like this. But it's connected carbon 2, and then there's a methyl group coming off it right there. But it's still 4 long, right? So this is 2 methyl, 2 propyl. It's a 2 methyl, 2 propyl group. And this is sometimes called isobutyl. Right? The other, I'm sorry, that's why I was getting confused. This is actually T-butyl. I was getting ahead of myself. It's actually this one here. This is actually T-butyl. T equals tertiary. Okay. The other option would be to do it like this. This is why I was confusing myself. Sorry about that. Again, it's 4 carbons long, so it'd be a type of butyl group, but the main chain of this side chain is 3 long, right? So it'd be a propyl. It'd be a 1 propyl, right? But the methyl is actually coming off of carbon 2, so it'd be 2 methyl, 1 propyl. It's kind of crazy. And this is the isobutyl. Right? So be aware of these. The big one's actually T-butyl. We're going to be using this a couple of different times. And instead of saying 2 methyl 2 propyl, I'll just call it T-butyl. Stuff like that. So, but you could name it. You're going to know all the rules to be able to do it. But again, so like that. So we're talking about the side chains. These are some of the hairier ones. But what we're going to next, right? So like that. So we're talking about naming these things in a minute, something like that. So one of the things you do know, sometimes we call it primary, secondary, tertiary, quaternary, right? So we saw this here, secondary and tertiary, something like that. That's just saying, so if you have a carbon, right, how many carbons are hanging off of it, right? So if you have 1 carbon, just, right, so this one here, right, how many carbons does it have? It has 1, so we call it primary, right? So this carbon, right, so if it has 2, right, that carbon is considered secondary. Right? If this has 3 carbons hanging off of it, right, as the trend goes, tertiary. Sometimes we do a 3 dot, or 3 degrees. If we have 4, right, that's considered quaternary. And it's going to be important, later in class to know if you're dealing with a primary, secondary, tertiary, or quaternary carbon, right? So they're going to have slightly different reactions that are associated with them, right? So it's going to be important for you to know. So you look at this, look at the carbon of interest, and say how many other carbons are hanging off of it, right? So if there's 1 carbon hanging off, it's primary. If there's 4, it's quaternary, right? So that carbon there has 1, 2, 3, 4 other carbons hanging off of it. It's quaternary, and everything else in between. Okay, so okay. Now next up, right? So these are the 4 rules. We're going to be talking about these rules a lot, stuff like that. So what we want to do, right? So for naming alkanes, okay, we're going to be using these 4 steps a lot, and we're just going to want you to know the 4 steps, and then know the different quirks of the different types of compounds that we're going to be working with. But primarily, we're going to be using these 4 steps. Okay, so the first thing to do is always have to find what's called the main chain. And in this case, it's the longest carbon chain, longest continuous carbon chain. You can't back up, you can't skip. You have to be able to put your finger on one side and count and put it down and go like this. You can't back up and go. It has to be a continuous chain. Okay, so from there, when you're going to find the longest continuous chain, go ahead and find that. I usually circle it, right? And that's going to be using your methane, ethane, propane, whatever. You're going to name it. Now, we've named all of those carbons. Okay, now we're just interested in the other carbons. Okay, so with that, from there, we're going to find and name the side chains, the branches off of there, the carbons that are branching away from it, not the ones on the main chain. Those are already numbered. Those are already part of the main chain. It's the carbons away from it. Okay, and then we have to find the attachment point, right? Which ones, right? So we can start from the left side and count 1, 2, 3, 4, carbon 1, 2, 3, 4, whatever. And then the other way we can do it is go from the right side, 1, 2, 3, 4, 5, right? When you add up those numbers, right? Whatever gives you the smaller number, that's going to be the one you want. That's the numbering you want to pick. Okay, so with that, so now you know the numbers, you know how many, what side chains are, you know the main chain. So let's assemble the name, right? So place the alkyl, the side chains in alphabetical order, and it doesn't, right? So ethyl comes before methyl, comes before propyl. Okay, now you put the attachment in front of the names of the individual, like so. If you have, if you have a propyl group coming off of carbon 4, right, you're going to say 4-propyl, right, because it's a number, usually number letter separation, so you just put a dash, right. Now, if you have the, and then 4-propyl, indicate how many of each type you have. So if you have 2 methyl groups, it becomes dimethyl. You still have to put the numbers out front, separated by a comma, right, and you put them in numerical order, right. So it'd be like if you had 2, 2, 3, right, so it'd be 2, 2, 3 dash trimethyl. Okay, now that di, tri, whatever doesn't take into account when you're doing the alphabetical order, right? So ethyl always becomes butyl comes before ethyl, comes before methyl, comes before propyl, right? So butyl is going to, right? So the ethyl is going to come before dimethyl, right? So you still have to compare ethyl, methyl, whatever. That, okay, and then from there, and then you put the parent chain at the end. Okay, so we're gonna do this. These are the 4 steps: find the longest chain, find the side chains, get the numbers, assemble the name. We're gonna be doing this a lot. Okay, so here we go. So we're gonna draw this out. Right. So don't forget, I would do the dots. You know, while you're still learning this. Okay, so I've transposed this on here. Okay, so first thing we had to do, step 1, find the longest chain, right? So here you go. You can go 1, 2, 3, 4, 5, 6, 7, 8. It's usually the easiest thing to go ahead and just try the horizontal first. At least gives you a baseline for what you need to do. Now, don't forget, you can go down these side chains, right? So you can go 1, 2, 3, 4, 5, 6, 7, right? You can also start over here, right? 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so here's the longest chain, right? I didn't go down here and then come back up. You just go right along here, and you should be nice and smooth, right? So here we go. So here's our main chain. And I usually circle it, right? Okay, so there's the main chain, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So it's C9. So that would be a nonane. Okay, so we've named those 9 carbons. Now we have to deal with this one, and these guys here. Okay, so this one here, it's 1 carbon long. You do not count that one. That is part of the nonane. You it's just how many are off of there, right? So that's a methyl because it's 1 carbon long, right? This one's also 1 carbon long, right? And this one is 2 carbons long. Remember, you don't count that, you just count these 2, right? So this is an ethyl because it's 2 carbons long. Okay, now we need to figure the numbering, right? So here we go. So we're going to assume this is carbon 1, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we assume that's the numbering, right? So this methyl group would be attached to carbon 3. This one's a carbon 5. This one's a carbon 6. Okay, the other option would be to say this is 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So in that case, for the blue numbering, this one's at carbon 7. This one's at 5 again. This one's at 4. Right? So what you do is you just add them up. Right? So it's 11, 14. And this is 11 and 16. You're going to pick the numbering that when you add them up gives the smaller number. So these are the numbers that you're going to do, that you're going to use. Okay, so the next question is, which comes first, right? So we're doing the numbering, right? Determine the attachment points. Okay, so we did that. Okay, now let's construct the name, right? So which comes first, ethyl or methyl? Well, ethyl comes first alphabetically, so we're going to list that, right? So it's going to be 6-ethyl, right? Now we put the attachment points, right? So it's 3, 5, right? There's a methyl group at carbon 3, a carbon at carbon 5, right? So we have 2 of them, right? So we need dimethyl, right? All right, so if you have a di here, I need 2 numbers out here. Even if they're attached to the same carbon, I need 2 numbers. Okay, you can't. Don't make me assume stuff like that. So it's 6-ethyl, 3-methyl, right? So we have all of our side chains taken care of, and then we put the main chain, no name. Okay, you can always check, right? First thing, so if you were to draw this out, usually you go backwards, right? So we have, what do we have? We have a main chain that's 9 long, right? 9 long. Hey, we have 2 methyl groups, right? We have one that's attached to carbon 3, right? If you use the black numbers, carbon 3, another one attached to carbon 5, right? And we have an ethyl group attached to carbon 6, right? So you can always go back and double check, right? So does this make sense for what was drawn up here? Okay, so there you go. So let's do some practice problems. Okay, so here we go. Put on the dots. Okay, so first things first, right? We need to do the main chain, right? So always start with the horizontal because it's the easiest. 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, 7. Oh, there we go. 1, 2, 3, 4, 5, 6, 7. Okay, now it wouldn't actually matter which of these 7 you picked, right? So if you start here or here, but just out of habit, I'm going to pick the horizontal one. But you could have started up there as well, so it does not matter. It's going to give you the exact same name, right? So be careful. That's your main chain, right? So here are our side chains here, right? So there's actually 4 methyl groups. So methyl, 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 right? Okay, so our main chain, right? So it's 1, 2, 3, 4, 5, 6, 7. So it's C7, right? Which would be heptane. Okay, so we have the 4 methyl groups, right? So if we're going to start on the left side, right? So it's 1, 2, 3, 4, 5, 6, 7, right? So it would be methyl group at 2, methyl group at 3, methyl group at 4, methyl group at 5. Okay, but if you're going to start here, it would be 1, 2, 3, 4, 5, 6, 7, right? So now we're starting, assuming this is carbon 1, right? So then it would be 3, 4, 5, 6. Okay, if you use the blue number. Okay, so let's add these up, right? So this is 5, 5, 14, right? 15, 18. Just add them up. Okay, so this gives us the smaller answer. So these are the numbers we're going to pick. Okay, so so we had to put the side chains together, right? So they're all methyl, so we don't have to worry about we don't have to worry about the alphabetical, right? But we have 4 of them, right? So it'll be tetra. So it'll be tetramethyl. So it'd be 2, 3, 4, 5 tetra, because we have 4 of them, methyl heptane. Okay, so we have a main chain that's 7 long, right? 1, 2, 3, 4, 5, 6, 7. Okay, and we have 4 methyl groups, right? If we use the black numbering, right? So we have one hanging off of carbon 2, carbon 3, carbon 4, and carbon 5. So there we go. So there's our double check. So there we go. Okay, so here we go. Right, so we're going to do this middle example here. Right. 1, 2. This one's fairly easy. Right. Again, it's just showing you the importance of going from either side. Right. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so as long as you pick, you include these guys, you get 8 long, you'll be okay. So just out of habit, I'll do the main, I'll do the horizontal, right? So there we go. So it's C8, so it'll be octane. That's our main chain, right? So here we go. We have 3 methyl groups, right? So methyl, methyl, methyl. Right, so again, so if we do the left side here, right, so it'd be 1, 2, 3, 4, 5, 6, 7, 8, right, so this methyl group would be 2, this would be 6, this would be 7, right, and if we go from the right side, it'd be 1, 2, 3, 4, 5, 6, 7, 8, right, so here, this one would be 7, this one's hanging off. For the blue numberings, right, this is 7, this is 3, and this is 2. Okay, so again, add them up. So that's 13. That'd be 15. Right? So this one, and this would be 12. So now, right, we're going to pick this one, this numbering, right? So because it gives the lower answer down here, right? So again, we have 3 methyl groups, right? So it's going to be trimethyl, right? So we're going to have 2, 6, 7. Oh, oops, wrong one. 2, 3, 7, right? Sorry about that. I'm going to pick the blue numbers. Trimethyl octane. So there we go. Right, we have a main chain that's 8 long. 1, 2, 3, 4, 5, 6, 7, 8. Right, and if you use the blue numberings, right, you have a methyl group of 2, 1 at 3, 1 at 7. So there we go. Okay, last one. Now this one's a little tricky, but not too bad. We have to apply some common sense here. Okay, so here we go. So I'm going to put the dots in. Okay, now, here's the problem, right? So we can go 1, 2, 3, 4, 5, 6, 7. Or we can go 1, 2, 3, 4, 5, 6, 7. Okay, so we can do this chain and have this big 2-butyl group. Or, what I prefer, is to go ahead and just use these guys here. There, so 1, 2, 3, 4, 5, 6, 7, right? So then you have, right? So then what do you have for side chains? You have methyl, methyl, methyl. So methyl, methyl, ethyl. Okay, so again, you could do this horizontal chain and this T-butyl, but this one here, 1, 2, 3, 4, 5, 6, 7 would also work as well. So here we go. So 1, 2, 3, 4, 5, 6, 7, right? So it's C7. So it'd be heptane, right? And if you use the black numbering, right, it'd be 1, 2, 3, 4, 5, 6, 7, right? So it'd be each of these methyl groups is hanging off of carbon 2, and the ethyl's at 3. Right? We did the blue numbering from this end, 1, 2, 3, 4, 5, 6, 7, right? So now the methyl groups are at 6. Each of these are at 6. This ethyl group's at 5, right? So if you add them up, right, that's right. So 4, 7 versus 12, 17, right? So we're going to use these numbers here, right? So now what do we do? Right? So we need ethyl versus methyl, right? So ethyl's going to be first, so it's going to be 3 ethyl, right? And now even though they're on the same one, you still have to say 2, 2, right? We can't assume that if one's at 2, the other's at 2, right? You need to not make me guess, right? So that when I'm grading an exam, right? So 2, 2. If you have a die here, you need I need 2 numbers here, right? And again, even though this is dimethyl, right, it comes after because methyl comes after ethyl. Doesn't matter about the die, okay? And then put the main chain at the end, heptane. So there we go. Okay, so what are the properties of the alkane? They don't really do a whole lot, stuff like that. So I mean, they're important, but they don't do much. And their unreactivity is good, right? Because we can use them as solvents, right? So we can so that works well. The other thing that they can do is they do burn really well, stuff like that, right? So gasoline, the gasoline used for your car or diesel or whatever, those are going to be those are mostly going to be alkanes, right? So everybody so if you're going to burn this, right? So you have your hydrocarbon here, you add oxygen, and out your exhaust pipe you get carbon dioxide and heat and water, right? So like that. So this is the main one that ends up happening. You can also get this you can also use halogenation. You can also use UV light to break these apart. So if you want to UV light will actually break the chlorine-chlorine bond there into radicals, right? So one electron will go with each carbon, and then from there it can actually extract a hydrogen and then react back and do here. But this doesn't happen very often. It's kind of a messy reaction, but it's something that can actually happen with that. So okay, so properties of the alkane, pretty much the longer the chain, the higher the melting and boiling point. It's there's some quirks down here, but that's pretty much the trend, right? So down here, right, so very short, so it's going to mostly be gas at room temperature, from about 5 to 8 or 9, right? So like that. So it's going to be right. So 100, well, say 50 degrees, right? So it's going to be mostly right. So in here it's going to be a liquid, right? And larger waxes, it's going to be you're talking about having solids, stuff like that. So the longer the chain, the more likely it goes from gas to liquid to solid, stuff like that. So at room temperature. So okay, so here we go. So we're going to break out our model kit here, stuff like that. So what's going to happen is we're going to be talking about the conformations, right? So for here, right, we have our model kit, right? So here's a 2-carbon piece, right, for ethane, right? Stuff like that. So the nice thing about carbon-carbon single bonds is that they can rotate in space. So right, so as long as you have a single bond, right, you can get rotation here like that. And so no big deal, right? So you can do this with your model kit. They move all around, stuff like that. So right, so they can be like this and around. Okay. Now, one of the things that actually happened is an interesting sort of view of these ethanes is that if you look straight down the bond, you can actually see the carbon behind it, right? So here we go. Right? So like that. So sometimes, right, so these carbon groups, right, so the hydrogen groups, right, so they can either be between each other, in that case, or right, they could actually be rotated so they're right behind each other, right? So like that. So so this is one way that we can do this. Look right down a carbon-carbon bond, right? So in this case, right, so the green ones would be the ones out here, the carbon out in front, and then the carbon behind would have those red hydrogens on here. So they would be the ones down here, stuff like that. So okay, and one of the things I notice is as this rotates around, you're actually going to get some these hydrogens. While they're pretty small, they can actually interact with each other between these 2 carbons, right? So here they're small enough so when they're what are called staggered, so that they are actually, so this hydrogen is actually in between these 2 hydrogens. There's no interaction. Okay, so this is called a staggered configuration. Okay, so when they're sort of offset by 60 degrees. But right, we said that these can rotate, so sometimes they're going to be right on top of each other, right? So in this form, what's actually going to happen is you're going to get some interactions here, here, and here. Each one of those is worth 4 kilojoules per mole, right? So this total, so if you were to add them up, it would actually be 12 kilojoules per mole of total strain. Okay, so strain means two groups knocking heads. Okay, right? So you just add it up each of the individual contributions to know the total, right? So this is eclipsed, and so this is called an eclipsed, staggered, right? Eclipsed, staggered, eclipsed, right? So you can actually do this, right? So as it goes around, right? So we have an eclipse, which would be high, would be 12 kilojoules per mole of extra strain, down to eclipsed, up, down, up. As you rotate this around, right? You would go around, up, down, up, down, up, down. Okay, by 12 kilojoules per mole, as it goes from eclipse to staggered configuration. Okay, so not too bad. You just add them all up. Each one of those is worth 4. Okay, but let's add propane. Let's add a propyl group to it. Okay, so right there. Here I'm going to use the red balls, so like that, just so it's a little bit easier to see. So let's put a methyl group on here. Right? It's going to be a lot larger than a methyl group, right? It's going to be swinging around out here, right? So, but when there's right, but when it's staggered like this, there's still no this methyl group is still small enough that we don't have to worry that there's no strain between them, right? But certainly when they're like this, right? So when they're eclipsed, now you still have these hydrogen eclipsing interactions. Those are worth 4 kilojoules per mole. Now this one here, between the methyl and the hydrogen, when it's eclipsed, that's worth 6 kilojoules per mole, right? So in this configuration, right, so we would have 4, another 4, and now 6, right? So instead of 12, right, we have 16 of total strain, right? So like that. So again, it would go, what was it? 14, 0, 14, 0, 14, 0, as the bond circles around. Okay, so now next up is, let's say we had, let's put a methyl group down here. So now it's butane, right? So 1, 2, 3, 4 carbons on it. Okay, so now we're going to have some issues, right? So here, so we're going to talk about a couple things, right? So we have eclipsing, right? So they're eclipsed or staggered, right? But we have this very special case where the methyl group's down here, one's going up, one's going down, right? So they're exact opposite. We actually call that anti configuration, but it's just a special case of a staggered configuration, right? But what can happen is, right? So right before, we said methyl, right? So in the eclipsing reactions, right, we have methyl hydrogen. So each one of these is worth 6. In this configuration, you would have another 4 from this one, right? So 6, 12, 16, right? With that, if you had it eclipsing like this, now this is really bad because you have 2 big methyl groups knocking heads, knocking into each other, right? So now this interaction here, this eclipsing is actually 11 kilojoules per mole. Okay, so with that, so this, each one of these guys, these methyl, would be 4, right? So 4, 8 total, and then this one here, which is 11, right? So this configuration would be a total of 19. So, but the problem is, even when they're staggered like this, okay, so they are still staggered, but the methyls are still right next to each other. So there's no, right, so we said, okay, in this staggered configuration, the hydrogen is small enough that it doesn't interact with the methyl group, and certainly the methyls, or the hydrogens are small enough that they don't. But when we have this interaction here, a staggered methyl interaction, this is actually what's called a gauche reaction. We don't really know why it's called gauche, but it's called a gauche. But this one's actually worth 3.8 kilojoules per mole, something like that. So instead, as you circle this around, what will happen is, right? So I think I showed, yeah. So right, so you have 19, right? So when we start with the anti down here, this would be no strain energy, right? So as you cycle this around, right? So that's, you have this interaction, you have this interaction, you have this interaction. It's worth 16. Now when you circle it around here, right, these steric interactions here aren't there, but you still have one here for where it's this gauche interaction here, right? So that's worth 3.8. Now let's cycle it another 90 degrees. Now we've got the maximum, right? So we still have this 8 here, or the 8 here from these methyl eclipsing. We also have this 19 here, stuff like that. So total, because this is worth 11, right? So now we're going to go back to the gauche, eclipse, regular, or anti, right? So like that. So you can sort of calculate it. And as you go around, right, you just calculate. You need to know the 3.8, the 4, the 6, and the 11, right? And we just calculate that each one going around. Okay, so if we wanted to do an example, right? So if we had, let's say we had this Newman projection, right? So off the back, carbon we had 2 methyl groups, and this one we had, and the front one we had 2 methyl groups, right? So when it's staggered like this, just add up each individual staggered configuration, right? So this would be 3.8, right? Methyl gauche, methyl gauche. This one's too small, so it's 0. This one's too small, so it's 0. This one's 0. This is 3.8, right? So it'd be 3.8, 3.8. There'd be there is just 3. Sorry, these 3 gauche interactions, you just add them up, right? So that's 4, carry the 2, it's 9, be 11.4 kilojoules per mole for there. Now, if we were to rotate this around, right? So we move this there, right? So we'll keep this carbon where it is. We're going to move the back carbon 60 degrees clockwise, right? So now this one goes right behind, so I'm going to indicate that that's right behind. So this one, if that one comes up there, that one comes down there. Right? And then this one goes there, right? So now we have these 3 eclipsing interactions, right? This is worth 11, this is worth 11, this is worth 4, right? So it's 11, 11, 4, right? So 6. So this is 26 kilojoules per mole, right? So even if I would suggest when you're doing the staggering, right? The staggering configuration, go ahead and just look at each individual one, right? Go all the way around, even if it's 0, just so you don't accidentally miss one. For eclipsing, you just need to worry about these 3. Okay, so there you go.